Thank you, Sue, and hi, everyone. Okay, so let me delve into it because the time is short. So I'm going to be first talking about experimental design, and I want to start off with a real example, which is that one of the students at our university came over to me and basically said that he's going to be doing an experiment where he's going to study yield and nutritional quality under future climate conditions. And when I say a future climate condition, this is a case in the future we project that the carbon dioxide level is going to increase and the temperature is going to increase. So that's the basis of the experiment I'm going to be talking about. And particularly, I'm going to be focusing on the computational aspects of generating experimental design. So I had a literature review where I kind of looked at the survey of like different experimental design R packages. And one of the most downloaded R packages is called Agricola. And the way that Agricola designs its functions are that we have these functions that have a prefix design dot, and it's followed by some acronym of the corresponding name design. So we've seen from Rosemary's talk, randomized complete block design. So that corresponds to design.rcbd. If you have a complete randomized design, you got design.crd. If you've got split plot design, design.split, Latin square design, design.lsd, and so forth. So you kind of get the picture, and this is something that we would call a recipe. Design from a menu of name designs. Now, it is easier to implement when you take this approach. However, what happens is that when you take such an approach, you're more likely to think about trying to get your experiment to fit one of those recipe designs, instead of actually trying to tailor your experiment designs to the resources that you have. So this sentiment is shared by our previous speaker, Rosemary, as well, in her book. She writes that, good design considers units and treatments first, and then allocates treatment to units. It does not choose from a menu of named designs. So yes, absolutely, but what can we do? So this is where I propose an alternative approach, which I refer to as a composable approach. And this is implemented in the package called Edinburgh. So how does it work? Well, in the first instance, what happens is that I'm going to initialize a design object and I give a brief context. So here I just say, you can see the function design, and I'm just going to briefly write that this is about a wheat yield and nutrition study. In the next step, I'm going to think about the units, just as Rosemary mentioned in her book, right? Think about the units first. What do I have? So talking to the student, he tells me he's got 4 glass houses, and within each of the glass houses, what happens is that there are 4 blocks. And you can see that written out in the code. I'm setting it so the glass house, there are 4 of them. Block is nested in the glass house, and there are 4 of them. And then within each of the blocks, I can fit 20 pots. And then we got that pot equals to nested in the block, where there's 20 of those. So you can see that this is a hierarchical kind of structure within the units. It's specified in code in the way that you see up on the screen. And the names of the argument there are completely flexible. So you might as well pick a name that actually corresponds to your own context. In the next step, I think about the treatments. So what is the treatments for this particular experiment? Turns out it's a factorial experiment. We've got carbon dioxide level, and he's looking at 2 levels. He's looking at the ambient one, or we're looking at the future climate, so that's where carbon dioxide is going to be higher. Temperature is also 2. So we've got the current temperature and the projected high temperature. Now, he wants to see that the result is going to hold, of course, to more generally. So he's going to look at somewhat of a diverse panel. So he's picking 20 genotypes for his experiment. And you can see that specified. And then lastly, after we consider units and treatments, we need to think about how those treatments are allocated onto the units. And this is what's specified here, where we've got the interaction of carbon dioxide and temperature applied onto the glass house, because there is an inherent constraint in the way that these treatments can be applied. You can't vary the level of carbon dioxide and temperature on a pot level. It has to be applied on the whole glass house, and that's what we see there. Genotype is something we can vary based on each of the pots, hence where I'm assigning the genotype onto the pot. Now, this whole experiment, if you were to give a named recipe, this is commonly referred to as split plot design. Now, when you use this framework, at the very end, there's the design object contained in this DES. And when you print that out, essentially what happens is that you've got an experimental design table. And that's what the package Edible stands for. It's an experimental design table. And you can see every column corresponds to one of the factors that we've defined, and then every row corresponds to an experimental unit, so you can see how the treatments were mapped onto a particular unit. So that's an experimental design. And the next step, I want to talk about simulating data for the given experimental design. And why would you want to do that? Well, simulating data allows you to simulate the whole analysis workflow, and you can use that as another way of refining your experimental design. Now, that's not a groundbreaking idea, and we've got people thinking about that. In particular, Banchik and co-authors have written a paper of how you can simulate plant breeding experiments using AlphaSim-R. And in that paper, they've outlined 7 steps in order to do the simulation for various plant breeding situations. So I'm not going to go through each one of these steps, but thinking about the overall workflow, if you are a user and then you are thinking about simulating the data for a plant breeding program, you first of all need to gather all the details associated with the program itself. Then in the next step, you have to translate it into code, and then there are decisions that you have to make. In particular, you need to think about the global parameters that you're going to define. So these include, for example, how many chromosomes there are for the particular species that you're looking at, the number of QTLs, and some of the effect sizes and variances corresponding to that as well. Now, what is desirable in the workflow is that there's a level of automation. If things were automated, you can make a quicker decision, and also it reduces the cognitive burden on the practitioner. If you can hide the data generating process from the analyst, that is more mimicking what happens when you get a real data. So there's some bias that potentially can come about if you actually know what the data generating process is. So there's an advantage to actually being a bit blind to it in the first instance. But you still want to have an option of peeking into that data generating process so that you can allow for validation. So that's what we want. And ideally, we want this entity, which I'm showing by this icon over here, where this will take in some kind of details and then basically do the second part of translation of the code and doing some level of decision making for you. So I thought here, why not try to leverage the usage of large language models? So this is quite new. You may have heard about ChatGPT. But essentially, these large language models employ a very complex architecture that's been trained on large corpus of text. And it's basically designed to mimic reasoning. And so with enough proper training, it can, with some care, bridge the gap between the analyst and the domain knowledge. Or you can be acting as a second opinion to yourself, again, with care. So I thought about trying to leverage this. And so as a proof of concept, I tried to combine the composable design of experiments approach with a simulation pipeline from AlphaSimR with a large language model in between to talk between it. So this prototype is available on my GitHub. So if you want to check it out later, you can look at the code. So first of all, I do need to specify what traits I'm interested in recording. So that's a feature of Editable, and here I'm saying that I'm gonna take look at the records, look at recording the yield on the pot, and then I'm looking at also measuring nutrition on the pot. So if you remember, this object was an Editable design, and it had the context of the pre-breeding wheat experiment under future climate conditions from what we saw before. And here, just when I set the traits, all I'm doing is saying that, look, I'm measuring yield and nutrition on the pot itself. There's no additional information I've given. Now, in this prototype called pbs.prototype, it only has like one key function. And what you do there is that you can just pass on an edible design. And so this object, desr, knows what traits you're trying to measure. It knows the brief context around the experiment, and it has the experimental design as well. And what happens next is then it's going to call up on the large language models behind the scenes. And then looking at the description that's been provided, it identifies it's a wheat, and it assumes there's 42 chromosomes, assumes that it's a hexaploid, and let's see if I can scroll, yeah. And then so it makes certain decisions for you and starts running AlphaSimR, and at the very end, what happens is that you've got some kind of trait that's been simulated. Now, you can add more context. So you might go, no, it's not a bread wheat, it's actually a durum wheat. So I'm just adding a brief context and say, well, the wheat used is actually durum wheat. Again, really, really low burden on the person who's using it, but I'm trying to leverage what's, basically like an entity that has a lot of information. And then from there, it recognizes it's a durum wheat. It says that, okay, it's 28 chromosomes, and assumes tetraploid, and then generates a simulated data. So key takeaway, and I might be running out of time, so just very briefly, first of all, composable system, I think it's a good idea. In silico experiments, to refine your design or breeding program, good. And then lastly, large language model, and it's okay. It's got potential, but definitely there's a lot more work to do to be able to harness it and use it for really simulation. So if you want to look at the slides, it is available in the link that's provided. And if you want to look at the software, they're all publicly available on my GitHub. Particularly Editable is available on the CRAN, so check it out. And if you have any questions, feel free to ask or come and talk to me.